Humanoid robots are no longer a future headline. They are the headline, right now, evolving faster than markets can price them and regulators can control them. This past week felt like a turning point the industry will look back on for decades. A compressed explosion of breakthroughs, uncertainty, commercial pressure, and legal turbulence that collided all at once. The narrative around humanoids has shifted from "can they move like us?" to "are we ready to live and work beside them?" Because while AI models race ahead in silicon, humanoid robots are racing ahead in steel, lithium, torque, factory contracts, logistics throughput, and now even courtroom claims, forcing society to ask the hard questions that were once academic, theoretical, or comfortably distant. This week alone, robots prove they can walk farther than most humans want to, flip like Olympic gymnasts, shoot baskets with AI-calculated trajectories, perform automotive assembly tasks beside luxury car frames, run entire warehouse workflows without human hands guiding them, and trigger aggressive price competition that until now only existed in the world of AI software. And yet, every leap forward made one truth clearer. Capability is accelerating far faster than safety assurance, transparency norms, force limitations, and legal accountability frameworks. The result is a new era, one where robotics excellence and systemic risk share the same stage, not separated by years, but by minutes on a timeline. To understand the scale of disruption, we start with endurance, and with AgiBot A2, the robot that turned a long road into a world record. In an industry dominated by vertical leaps, flashy mobility demos, neural network tricks, viral parkour clips, and short bursts of proof-of-concept theatrics, A2 brought a quieter, more important flex: reliability under time, stamina under compute autonomy, and stability under physical degradation. It walked 66 miles, 106 kilometers autonomously from Suzhou to Shanghai. A journey that crosses urban outskirts, industrial infrastructure, temperature variation, public roads, micro-terrain irregularities, vibration cycles, structural fatigue risks, navigation unpredictability, battery discharge curves, and countless small physics violations that humanoids historically struggled to survive for longer than an hour. It maintained bipedal balance across the entire distance, proving that long-duration autonomy is no longer a lab experiment, that gate planning can generalize beyond flat indoor tiles, that power systems can scale to hours without failure, that motors can survive continuous load without mechanical drift, that onboard compute can self-navigate outside fenced areas, and that embodied AI can sustain sensor feedback control loops without a human resetting the stack. This walk mattered because it rewrote the metric of progress: endurance over spectacle, long-term locomotion over burst stunts, predictable stability over fragile agility, sustained autonomy over tethered remote operation, and measured engineering over choreographed hype. But it also mattered because it signaled that robots are inching closer to unsupervised public operation, walking into environments where GPS reflections bounce off skyscrapers, where footpaths shift unexpectedly, where a trip could mean system failure, and where batteries operating at 66-mile discharge cycles raise serious safety questions around overheating risk, thermal runaway, chemical stability, failure mode self-governance, pedestrian interaction, and the ability of a machine to make autonomous safety decisions next to public infrastructure shared with civilians. When a robot can walk farther than any commercial humanoid in history, that isn't just progress. It's a reminder that safety protocols can't assume short deployment windows anymore. From walking to flipping, the next benchmark came from the sky, not the ground. AgiBot M1 made it clear that physical dominance in acrobatic humanoid movement no longer belongs to just Boston Dynamics Atlas or Unitree's Agile systems. In a stunning evolution of dynamic physical robotics, M1 released footage of itself performing explosive acrobatic maneuvers, most notably clean backflips, executed with rotational stability, mid-air pose correction, high-torque push-off power, controlled angular momentum distribution, and flawless landing absorption, signaling that humanoid robots now operate in a physics envelope once thought too difficult for any new competitor to reach so quickly. A backflip for a robot isn't just a flip. It is a biomechanical symphony of torque density, actuator synchronization, EMU calibration, fall prediction modeling, motor load compensation, joint stress blending, power burst management, real-time posture correction, and landing force dissipation without self-destruction. M1 hit all those beats, becoming the industry's new challenger in high-velocity motion dynamics, proving that humanoids are no longer just mimicking human kinematics. They are exceeding typical human performance in controlled test environments. But acrobatic ability also reveals a darker mirror. Backflipping requires explosive actuation. Force bursts far beyond normal workplace motion, and high shock absorption at landing, which if unsupervised or deployed in mixed human environments without strict force guardrails, could pose serious injury risks. Acrobatic excellence makes the safety conversation louder, because when robots begin to operate in full dynamic motion envelopes, the risk is no longer about falling. It's about the force they might transfer into surroundings when a maneuver is miscalculated or applied outside of testing arenas. While engineering benchmarks climbed, market benchmarks collapsed. XPENG detonated the first publicly observable price shockwave when it revealed the commercial pricing of its female humanoid robot model Iron, unintentionally sparking history's first humanoid hardware price war. A market event that previously existed almost exclusively in AI model licensing and software subscriptions, but has now spilled into embodied robotic systems. Iron was positioned not just as a robot, but as a brand statement. Female humanoid framing, showroom elegance, prosumer curiosity appeal, and commercial positioning that made it feel less like a mechanical product and more like a character in a broader adoption narrative. The price reveal triggered immediate market response from competitors, accelerating commoditization timelines for humanoid robots, making them feel attainable to industries previously priced out, pushing accessibility beyond elite manufacturing contracts, and signaling the dawn of mass humanoid adoption economics. But when prices drop quickly, safety validation sometimes drops quietly in parallel. Hardware price wars compress margins, compress development windows, compress QA budgets, and compress safety investment cycles, creating a dangerous question. Are we incentivizing companies to compete on human safety metrics, or only on affordability and viral spectacle? Because accessibility democratizes adoption, but it also democratizes exposure to poorly enforced safety, especially when deployment shifts from premium industrial contracts into prosumer commercial channels where force limit transparency, structural reliability, uptime accountability, control system governance, and public co-working certifications don't yet exist in globally agreed formats. The very thing that makes humanoids adoptable, lower cost, is also the very thing that could make them dangerous if safety investment is still optional instead of mandatory. Then came the industrial insertion, a premium deployment milestone shadowed by premium legal questions. Figures humanoid robots entered real BMW production lines, operating directly on automotive assembly workflows. A breakthrough for embodied AI entering high-precision, high-stakes, high-throughput manufacturing environments where tolerance for error is microscopic and cost of failure is enormous. These humanoids aren't carrying basketballs or walking roads. They are working beside luxury car frames, conveyor belts, assembly sequencing, factory floor IoT stacks, human monitoring zones, robotic arms, torque calibration systems, metal fabrication environments, and live automotive supply chain dependencies, showing that humanoid AI can function inside real industrial workflows, not just simulation environments or staged robotics videos. This matters because the frontier is no longer mobility. It is labor insertion into real supply chains, the kind where uptime means revenue, robotics drift means defective products, and force miscalculation means human injury and legal liability. And for the first time, those legal questions went public, when a lawsuit alleged that figures humanoids were capable of exerting dangerously high-impact forces, claims metaphorically framed around serious injury potential, and a lack of transparent disclosure around robot force limitations, maximum impact thresholds, and enforceable co-working safety limits. The lawsuit matters not only for what it alleges, but for what it represents, the accountability vacuum. When robots and humans physically share work floors, the old question of AI safety changes domains. In software, a misprediction means wrong text. In robotics, a misprediction means wrong force. And yet today, there are no globally enforced public standards that define the exact maximum force a robot is legally allowed to exert during normal operational tasks when working beside human coworkers. No consistent certification body governing human-humanoid co-working compliance across assembly line environments. No mandatory forced telemetry transparency requirements for manufacturers deploying robots into premium industrial contracts. And no universal answer to the central question. If a humanoid exerts unsafe force and a human is injured, does liability belong to the robot maker or the entity deploying robots onto shared human floors? The uncertainty itself reveals a gap bigger than any robot could ever physically jump over. It is a policy and accountability chasm that means humanoid adoption is officially moving faster than the world can ensure, regulate, or legally arbitrate. The next moment hit not with force, but with precision. Unitree showed that simulation-trained robotics motion isn't future magic anymore. It's present-day execution. When its G1 robot demonstrated high-precision basketball shooting using NVIDIA compute orchestration and Carnegie Mellon's ASAP motion planning framework. A milestone in AI physics simulation frameworks merging directly into humanoid control stacks. This wasn't just a robot shooting a ball. It was a demonstration of simulation-trained motion primitives crossing into the real world without teleoperation. Trajectory prediction overlays embedded into motor planning. Neural motion frameworks deployed onto physical actuation stacks, and embodied AI executing skills learned inside digital AI physics engines that can compute movement better than human motion engineers manually scripting animations. This matters because it reveals the next frontier. Humanoids will learn tasks in simulation and execute them in real industry stacks without needing a human puppeteering every move anymore, which leads to an urgent safety question that flips the excitement on its head. If robots learn motion inside simulations, who validates that motion for real humans when a misprediction could cause physical injury, not simulated failure? Simulation-trained motion frameworks are optimized for tasks, not always optimized for nearby unstructured human safety considerations unless explicitly built into the framework. And right now, the industry does not have a universal global validation layer that guarantees that simulation-learned movements are safe once deployed next to real people, machines, and industrial surroundings. Sim-to-real learning accelerates skill adoption, but until safety validation frameworks accelerate faster than learning frameworks, this evolution adds as many red flags as it does milestones. And finally, autonomy closed the loop, but opened the question wider. Mentibot revealed the first fully autonomous warehouse workflow powered by humanoid robots handling navigation, shelving interaction, object manipulation, task sequencing, supply chain movement, aisle awareness, package handling, logistics dependency execution, sensor stack autonomy, and operational decision loops without humans remotely guiding every motion, proving that humanoid robots are no longer a novelty in controlled lab demos. They are labor systems entering real supply chains where unpredictability is real, floors are cluttered, aisles are narrow, humans cross paths without prior scheduling, payloads are stacked unpredictably, objects shift outside of perfect CAD placement, failure modes can mean real downtime, and miscalculated motion can lead to injury in environments not protected by test arena isolation. When a robot can execute an entire labor workflow without a human planner forcing sequencing, the question isn't capability. The capability is already here. The question is governance. If innovation is moving 10x, safety needs to move 20x, because adoption doesn't wait for regulation to catch up. This week forced a new truth into view. Humanoid robots have stepped out of simulated physics into real physics, out of tech showcases into market showcases, out of stunts into endurance, out of development timelines into price timelines, out of mobility limits into force limits, and out of labs directly into workplaces alongside humans whose safety the world still doesn't know how to legally guarantee, physically certify, or financially insure. The machines prove they can do the work, the companies prove they can drop the price, but the world still hasn't proven it knows how to cap the force, sign the liability papers, or validate human safety when steel steps onto shared floors, because embodied AI safety isn't theory anymore. It is real, human, legal, urgent, and unfolding faster than policy can breathe.